Hello everyone, my name is Wang Yuxuan. I'm from University of Science and Technology of China. It's a great honor to be here to share our work with you. Our work is about the single-channel regression-based speech enhancement. We introduced the NAMA architecture, that is, noise-aware memory attention network for this task, and achieve a performance improvement using a compact framework compared with the state-of-the-art model, dynamic noise-aware training. Next, I will introduce our work in detail. I will introduce our work in the following 5 aspects. First, I will introduce the background and motivation of our work. Single-channel speech enhancement is a widely studied problem in signal processing. It aims at enhancing noisy speech to improve speech quality and instability. In recent years, most supervised speech enhancement techniques have been based on deep neural network architectures, and our work is exactly based on LSTM-RNN, that is, long short-term memory recurrent neural network, which has a powerful modeling ability on the acoustic context of neighboring frames. Noise-aware training has been applied successfully to speech enhancement to deal with the mismatch exists between the training and testing sites. Notable approaches such as SNAT and DNAT. SNAT predicts the noise information and appends the same information to each frame by assuming that the noise signal during the whole entrance is stationary. However, noise is changing greatly in most realistic environments, while DNAT estimates the noise signal in a dynamic manner and is able to deal with the non-stationary scenes. However, DNAT is designed as a complicated two-stage model, and it can achieve a good performance over DNN, but when it turns to LSTM-RNN, the performance gain is less significant. To solve this problem, we propose a novel noise-aware memory attention network named NAMA to improve quality of enhanced speech in unseen noise conditions. Under the NAMA architecture, our noise-aware training is carried out jointly with the processing of the denoising. This one-stage model training design significantly simplifies the two-stage model design of DNAT. Moreover, the experimental results show that our NAMA model can still maintain significant improvements under the LSTM-RNN setting. Secondly, I will introduce our proposed deep NAMA architecture. This picture illustrates the NAMA structure consisting of the main network, the memory block, and the attention block. The key of the proposed framework is to generate predicted features incorporating the noise information embedded in the current noisy speech frame by a weighted combining of the noise basis vectors in the memory block. With the help of the attention mechanism and LSTM-RNN, the predicted noise vectors can provide useful information for speech enhancement. Next, I will introduce these 3 modules separately. Let's first focus on the main network. Here, LSTM-RNN is adopted as the main network for its congenital advantage of sequence representation and temporal context acquisition. The main network has 2 effects on the whole framework. One is the denoising, that is, removing the noise from noisy speech to get the enhanced speech, and the other is exchanging information with the attention block. We next turn to the memory block. It consists of an extensive set of basis vectors, which contain rich noise information and can represent a new noise type by weighted combining. Here, we adopt the frame-level MFCC feature vectors extracted from noise signals as the basis vectors. The memory block provides the prior noise information for the attention block. The procedure of memory block generation is illustrated in algorithm 1. First, we need to collect different types of noise waveforms from different environments, such as fax machine noises, car idling, footsteps, paper rustling, rain, animal noises, etc. Second, we cut the noise waveforms into frames and extract the MMCC features. Next, based on those noise MMCC feature frames, we cluster them to form a compact set of k distinguishable noise basis vectors using a k-means algorithm with a cosine distance. Finally, the k cluster centers are stored at the memory block M. The vector M subscript k refers to the kth noise basis vector. We now look at the attention block. The attention block is another important part of the whole architecture. It serves as an auxiliary network and focuses on selecting the basis vectors from the memory block to improve the noise awareness of the main network. As we all know, the noise is removed gradually with the layers increasing. The attention block exactly needs the noise information to pick up the most relevant vectors in the memory block. So, we append the output of the attention block to the input features here. Besides, we perform frame expansion on the input features as formula A, where the vector x subscript t denotes the noisy feature vector at frame t. Vector f subscript t denotes the noisy feature vector after frame expanding at frame t. And tau controls how many history and future frames are involved. The attention model takes vector f subscript t and m subscript k as input and combines them to a vector with the learned weights. In formula B, the vector e subscript t and k score the similarity, and the attention value alpha subscript t and k is then calculated through a softmax operation as formula C, as shown in the dashed arrows of the picture. After normalization, the predicted noise vector C subscript t is calculated as a weighted sum of all the basis vectors as formula D, as shown in the solid arrows of the picture. And the new input vector is then performed by concatenating vector x subscript t and vector c subscript t as formula E. Until now, we have introduced the three modules completely. In the training stage, the parameters in both the main network and the attention block are jointly optimized. In the testing stage, the predicted noise vector concatenating to the input of the main network can be obtained by the attention mechanism. Thirdly, I will introduce the experiments about our method and analyze the corresponding result. First, let me introduce our experimental configuration. All entrances from the training site of Wall Street Journal corpus were corrupted with 958 noise types at 5 levels of SNR to build 36-hour multi-condition training site. The 330 entrances from the call test of Wall Street Journal corpus were used to construct the test set for each combining of noise types and 3 low SNR levels. 3 unseen non-stationary noise types, namely Buccaneer 1, Disjoiner engine, and HF channel, were adopted for testing in this experiment, which were collected from the noise X92 corpus. The LSTM configurations were fixed at 3 head layers. Each head layer had 1024 memory cells, and the output layer had 257 units. In the memory block, we set 500 noise basis vectors here, and we expanded the input to the memory block 3 frames forward and backward respectively. The 257-dimensional LPS features were produced to train the main network, and the 12-dimensional MMCC features, also noise waveforms in the training set, with their first and second order derivatives, were extracted as the basis vectors. This table lists the average PESQ, STOI, and LSD performance comparison of different models on the test set. Among the three measures, PESQ is designed for measuring speech quality, STOI is designed for measuring speech instability, and LSD is designed for evaluating signal differences in the frequency domain. Among these models, noisy denotes noisy speech with no processing. Mapping represents the original LSTM-based regression model using the direct mapping approach without noise-aware training. NAMAN denotes our proposed approach. Oracle means the real noise spectrum is known. Three low SNRs are selected where the enhancement task is hard and necessary to carry out. Both the two improved models, SNAT and DNAT, outperform mapping on all the three measures and SNR levels, and severely underperform Oracle, which leaves a lot of room to further improve the performance. Besides, NAMAN performs much better than mapping, achieving an average PESQ gain of 0.177, an average STOI gain of 0.029, and an average LSD decrease of 0.635. NAMAN also yields better results than SNAT, which cannot well handle the non-stationary noise types. What's more, even compared with the powerful model DNAT, NAMAN can also keep the consistent superiority, which is more obvious for low SNRs. PESQ improves with a gain of 0.145, STOI increases with a gain of 0.029 at SNR equals -5 dB. This picture shows the spectrograms of an entrance example corrected by Buccaneer-1 noise at SNR equals 0 dB. DNAT successfully removes most of the noise in the noisy speech. NAMAN not only reconstructs more speech details compared with DNAT, as shown in the dashed rectangular boxes, but also restores more information during high-frequency bands through the whole fragment, as shown in the dashed oval boxes. NAMAN really performs better in speech restoration and achieves less speech distortions. This table compares the runtime latency and the model size of different models. A set of 500 noisy test entrances are selected randomly and fed to the network to estimate the latency and the model size, which are normalized by the corresponding values of the mapping model. From the last two rows, we can observe that for both latency and model size, NAMAN uses only about a half of those values in DNAT. Next, I will introduce the conclusion of our work and our future work plan. In this study, we have proposed a novel noise-aware memory retention framework for regression-based speech enhancement. Compared with the two-stage DNAT model, NAMAN can predict noise information jointly with the denosing process. Experimental results show the proposed NAMAN approach consistently achieves better performances in low SNR conditions in terms of PESQ, STOI, and LSD than those obtained with DNAT. Furthermore, NAMAN has the distinctive advantages of simple structures and better generalization ability on mismatched conditions. In the future, we plan to expand our model with SNR-aware and speaker-aware training, which may embody complementary capabilities for speech enhancement. Finally, Thank you very much for listening to our work here. If you have any questions, welcome to ask and I will ask them.